Hello, and welcome to our Vehicle Thermal Management Research presentation. My name is Ben Brito, and my teammates are Logan Mulvey, Malharsain Solanki, and Joseph Wood. Our topic is the transmission of electric vehicles. A traditional internal combustion engine requires multiple gear ratios to keep the engine in an RPM range in which it produces sufficient power or efficiency. Electric vehicles do not require this because the torque provided by the motor is much more consistent over a large RPM range. As a result, most electric vehicles utilize a single-speed transmission. Although multiple ratios are not required, research is being conducted to determine whether they can offer improved efficiency and performance. The three most promising options are the single-speed, which is currently used in most vehicles, a two-speed, which simply offers a second gear ratio, and a continuously variable transmission, or CVT. A CVT offers an infinite number of ratios within a range, allowing for continuous power delivery with no interruption required to shift gears. The basic working principle is that power is transmitted through a belt, which is mounted on two pulleys which change diameter to vary the gear ratio. They have been widely available on ATVs and snowmobiles for many years, and have recently become more common in the automotive world. Three research papers were studied to generate this presentation: experimental study of electric vehicle gearbox efficiency, experimental research of transmissions on electric vehicles' energy consumption, and development of continuously variable transmission and multi-speed dual clutch transmission for pure electric vehicle. Experimental study of electric vehicle gearbox efficiency covers the study of a single-speed transmission. The objective of the experiment was to determine the overall efficiency of the transmission as a function of input speed and torque. The subject of the study was a prototype dual motor drive system using gears and bearings from a Skoda MQ200 O2T transmission. It is rated for 200 Nm of torque up to 7,000 RPM and has an overall ratio of 5.857 to 1. The transmission was placed between two dynamometers, with one connected to the input and one connected to the output. The dyno connected to the input was simply used as a motor. This configuration led to two issues. The first was the limitation of input torque. Because the transmission is intended for a dual motor setup, each input was only rated for 100 Nm. The second issue was the requirement for a locking differential, as the output torque was only measured from one side. With considerations made for the configuration issues, the system was run from 500 to 3000 RPM, with 20 to 85.4 Nm of torque applied. The experiments were conducted with two different oil levels in the transmission. The first was 500 grams of oil, and the second was 820 grams. Results show that the transmission is relatively efficient overall, with the best efficiency found at high torque, low RPM, and less oil. The second paper is experimental research of transmissions on electric vehicles' energy consumption. It focuses on the efficiency advantages which can be acquired through the use of a two-speed transmission, or a CVT. Unlike in the last study, these transmissions were tested on-road in a vehicle. The test track was 240 meters long, with a full test consisting of 2 laps, or 480 meters. Several driver rules were put into place to ensure that the transmissions were tested under similar conditions. Additionally, the two-speed transmission was shifted at speeds of 8, 11, 14, 17, and 20 km per hour to determine the ideal shift timing. Data was generated by a custom data logger which measured power supply voltage and current twice a second. This allowed for power versus time graphs to be generated for the different transmission configurations. Overall, the two-speed transmission reduced energy use by 3.8%, and the CVT reduced energy use by 4.3%. It must be noted that the CVT was only tested for one lap, so conclusive data is unavailable. It is also noted that for the two-speed, shift timing is critical. Additionally, because the test only included one acceleration from standstill, higher efficiency gains are expected from city driving with more stop and go. The third paper, Development of Continuously Variable Transmission and Multi-Speed Dual-Clutch Transmission for Pure Electric Vehicle, discusses a study conducted to determine the type of transmission which offers the greatest benefits to energy efficiency, how many speeds the transmission needs, and what is the best shift timing for the transmission. Unlike the previous studies discussed, these results were generated from Simulink simulations. Two vehicle classes were considered: B-class compact cars and E-class full-size sedans. Single, 2, 3, and 4-speed transmissions were considered, as well as a CVT. Simulink models were developed using data from the EPA Highway Fuel Economy Test Cycle. A 4 to 5% efficiency loss is associated with adding a second gear, with another 2 to 3% added for each additional gear. Meanwhile, the CVT suffered an 11 to 22% efficiency loss. It was found that the two-speed transmission was superior to the 3 and 4 speeds due to reduced manufacturing costs and energy loss. It improved the energy utilizing rate of the B-class compact car by 16.4% and the E-class full-size sedan by 9.6%. The CVT, however, is the best option. It improved the energy utilization of the B-class vehicle by 17.4% and the E-class vehicle by 24%. In conclusion, it is noted that multi-ratio transmissions can have a positive effect on the efficiency of electric vehicles. It has been found that the two-speed transmission is the best option when using set ratios, but the CVT is the best option overall. Thank you for watching our presentation. We are happy to take any questions at this time.